It really makes you think, doesn't it? How we humans build this internal picture of the world.
Hmm.
Scott McCloud, in Understand Comics, he talks about these mental maps.
Right.
And J. Wright Forster had that idea that these models are always like selective, just a few key things we grab onto.
Yeah, just representing reality in a simplified way.
It's kind of amazing how much we depend on these mental shortcuts just to make sense of everything.
Well, what's really fascinating now is that we're seeing artificial intelligence start to develop something similar.
Oh,
We call them AI world models. You can think of them as like compressed versions of an environment that an AI learns so it can make smarter choices.
like giving the AI its own way to sort of imagine and predict things.
Exactly. It's building an internal simulation in a way.
Okay, cool. And that's exactly what we're diving into today then, this whole concept of AI world models.
Yep. How they learn, what they can do.
Yeah. And why this could be a real leap forward. So for this, we've got a research paper called World Models by David Ha and Jürgen
It's
Schmidher.
a foundational one.
And there's a Forbes article looking at how these models are changing things like generative AI and LLMs.
Right. The broader impact.
And also an NVIDIA glossary entry that defines something called World Foundation models. So quite a bit to chew on.
Definitely. So the mission here really is to get our heads around how AI learns to simulate and interact with environments using these world models.
Right. We want to figure out what makes this approach so significant and, is it really a shortcut to smarter AI?
Let's find out. Where should we start? The paper.
Yeah, let's unpack that world models paper first.
Yeah.
The core idea that really grabbed me was training an AI agent, unsupervised, right?
Right. It learns on its own.
To build this compact understanding of its surroundings, both like space and time, how things are laid out and how they change.
And the really clever bit, as you
Yeah.
said, is that once it has this internal model, it can use those learned features to train much simpler policies, simpler ways to decide what to do, more efficient.
Okay, so the paper talks about a specific agent model with like different parts.
That's right. Three main components. First up is the vision model, or V model. It uses something called a variational autoencoder, a VAE.
A VAE, okay.
Think of this as the AI's way of, well, processing what it sees.
Yeah.
It takes complex input, like frames from a video game.
High dimensional stuff.
Exactly. And boils it down into a much smaller set of key features. This compressed representation is called a latent vector, often denoted Z's.
So it's like squeezing a detailed picture down to its essence, losing some detail but keeping the important bits.
Precisely. The paper gives the example of training this VAE on screenshots from Vizdoom.
Okay.
And this latent vector, even though it's way smaller, they mentioned 32 dimensions for a car racing game, 64 for Doom.
Tiny compared to the image pixels.
Right. It can still be used to reconstruct the original image, pretty
Yeah.
much. And what's really cool is you can tweak the values in that latent vector and see how the reconstructed image changes.
So the AI has actually learned the sort of fundamental visual building blocks of its world.
You could say that, yeah. It understands the underlying structure. Okay, so that's the V model.
Got it. What's next?
The second part is the memory model, or M model. This uses an MDN-RNN,
Okay, another acronym, MDN-RNN.
mixture density network, recurrent neural network. Its job is basically to predict future latent vectors.
So predicting what the V model is likely to see next.
Exactly. But here's the thing. The real world, even virtual ones, can be unpredictable, right?
Sure. Random stuff happens.
So it doesn't just make one single prediction. Instead, it calculates a probability distribution over possible future states.
Yeah.
It figures out all the likely possibilities and how probable each one is.
Okay. So it's not just this will happen. It's more like there's a 70% chance of this, 20% of that, 10% of something else.
Precisely. It uses what's called a mixture of Gaussian distributions to represent that uncertainty. It makes the model much better equipped to handle the stochasticity, the randomness of complex environments.
That makes a lot of sense. They also mentioned adjusting a temperature setting.
Yeah, the temperature parameter.
Yeah.
That lets you control the model's uncertainty or randomness in its predictions.
Mhm.
Lower temperature, the model becomes more confident, more deterministic in its predictions.
More focused.
Higher temperature becomes more stochastic, more uncertain, exploring more possibilities.
Kind of like adding more variety to its imagination.
Sort of, yeah. They related to sketch RNN, which predicts, like, the next pen strokes when someone's drawing.
Yeah.
Another sequence prediction task with inherent uncertainty.
Okay, V for vision, M for memory, and prediction. What's the last part?
The final piece is the controller, or C model. This is the part that actually decides what action the agent should take.
Hey, decision maker.
Right. And the paper makes a point of keeping this model really simple, often just a linear model.
Linear. So not very complex at all.
Nope. It takes the current compressed vision info from the V model, that Z sector, and the memory model's prediction, or hidden state, as input. And based on those, it outputs an action.
So the idea is let the world model the V&M parts do the heavy lifting of understanding the world.
Exact.
So the controller can just focus on the core problem, which actions lead to good results. The credit assignment problem, they call it.
That's the core idea. Simplify the control problem by building a rich internal model first.
Okay, so the world model learns the what's and how of the world, and the controller just needs to learn the do this part based on that understanding.
Precisely. And to really show this works, the paper details that experiment in the car racing environment.
Right, the driving game.
Yeah. The goal is to steer a car around these randomly generated tracks using only the raw pixels from the screen as input.
Just the picture.
Just the picture. And the bar for solving it is really high. You need an average score of 900 over 100 consecutive trials. Very few mistakes allowed.
That sounds like a seriously tough challenge, especially from raw pixels. So how did they actually teach the world model about this racing world?
Well, first, they just let the car drive around randomly for a bit. They collected data from 10,000 random sessions, basically.
Okay, lots of examples.
Then, they trained the VAE on the frames from those sessions to learn how to compress each frame into that 32-dimensional latent vector Z.
Right.
After that, they used the sequences of latent vectors, plus the random actions that were taken, to train the MDN-RNN. Its job was to learn to predict the next latent vector, given the current one and the action taken.
And importantly, you said the world model didn't get any info about the game score, right?
Correct. Its only task was to learn to model the visual environment. Just predict what happens next visually.
Okay, so the world model learns the environment dynamics. Then how did they train the controller, the C model, to actually drive well?
They used an evolutionary strategy called CMAES. It's a powerful optimization technique that sort of mimics evolution to find the best parameters, the best settings for the controller. Lots of trial and error, essentially.
Gotcha. And they mentioned the controller was simple, right? Parameter-wise?
Very simple. Just a linear model with only about 868 parameters, I think it was.
Yeah.
Compare that to the VAE and MDN-RNN, which had millions of parameters.
Wow. So the complexity is definitely loaded into the world model, the V&M parts.
Absolutely. The understanding is complex. The action policy is simple.
So what happened? Did it work? How did the car drive?
Well, the results were really interesting. They first tried training a controller that only had access to the V model's output, just that latent vector Z's, the compressed snapshot of the current frame.
Just seeing the present moment.
Right. And the driving was, well, it was kind of wobbly, unstable. Yeah. The car could move forward, but it really struggled with sharp turns. It only managed an average score of around 632.
Okay, so just seeing isn't enough for smooth control.
Exactly. It highlights that key idea.
Yeah.
You need more than just a picture of the present to act skillfully, especially in dynamic situations. You need some kind of prediction or memory.
That makes sense. Like if you're driving, you don't just react to what's right in front of you. You anticipate the curve, right?
Precisely. So then they tried the full setup, the controller getting both the current latent vector Z's from the V model and the hidden state H from the MDN-RNN, which contains information about the predicted future.
Ah, giving it that predictive context.
Yes. And the performance improved dramatically. The driving became much, much smoother. The agent could anticipate turns, handle the track much better.
And the score.
It achieved an average score of over 906, which basically solved the task and was state-of-the-art at the time for that benchmark.
That's fantastic. It really shows the power of having that predictive memory component.
Absolutely. The researchers draw that analogy to experienced human drivers who make these seemingly instinctive decisions based on their deeply learned internal models of physics and road dynamics.
Yeah, that fits. The paper also mentions something called car racing dreams. What's that about?
Yeah, that's cool. Once they had the trained world model, VM, they could basically run simulations inside the model itself.
Like generate hypothetical race footage.
Kind of.
Yeah.
Generate sequences of future latent vectors based on actions. They could then put their trained controller into this dream environment and just watch how it behaved without interacting with the real game at all.
It's like the AI is rehearsing or imagining scenarios in its own head.
Pretty much. And that leads directly to the next really fascinating experiment they did. Learning inside of a dream. This was in the Viz-Doom environment.
Okay, the first-person shooter game.
Right. Here, they took the dream idea a step further. Instead of just observing, they actually trained the controller entirely within the simulated environment generated by its own world model.
Whoa, wait. So the AI learns to play a game that exists only inside its own internal simulation.
Exactly.
Yeah.
In this setup, the V model wasn't even used during this hallucination or dream phase. The M model, the MDN-RNN, was responsible for predicting everything. The next latent state Z, and whether the agent dies in the game, the done signal.
That's a wild concept. So how did they set that up?
Similar initial steps. Train the VAE on game frames, then train the MDN-RNN to predict the next latent state and the probability of dying based on current state and action.
Okay.
Then, they essentially built a virtual Viz-Doom environment using only this trained M model. And they trained the controller using reinforcement learning entirely within this generated simulation, rewarding it for surviving longer.
So it never even saw the real Viz-Doom game during its controller training.
Not during the controller training phase, no. It was all done inside the dream.
Did it work? Did the agent learn anything useful just playing in its head?
It absolutely did. The controller learned effective strategies to dodge fireballs within that simulated dream environment. But here's the kicker. When they took that policy, learned entirely in the dream, and transferred it back to the actual Viz-Doom environment,
Yeah.
it performed remarkably well.
Yeah.
It successfully avoided fireballs in the real game. In fact, it often performed even better in the real game than it did in the dream environment it was trained in.
Better in reality than in the dream. How does that work?
The thinking is that the dream environment being generated by the model was probably a bit noisier or more unpredictable than the actual game.
Ah.
So training in that slightly harder, more chaotic virtual world made the agent more robust, more adaptable when it faced the somewhat cleaner dynamics of the real game.
That is so counterintuitive, but really cool. Like practicing with the difficulty turned up makes the real thing seem easier.
Exactly. It suggests this dream training approach could be really powerful for building robust agents.
But surely the dream isn't perfect. The model must have flaws.
Good point. And they encountered exactly that. They called it cheating the world model.
Cheating.
Because the world model is just an approximation, right? It's not perfect reality. Agents, especially during training in the dream, can sometimes discover and exploit imperfections or loopholes in the model.
Ah, like finding a glitch in the simulation.
Sort of. For example, in the Viz-Doom dream, the agent sometimes found weird sequences of actions that could, like, prevent the simulated monsters from even shooting fireballs in the first place, something that wouldn't work in the real game.
Okay, so it finds ways to break the simulated physics or logic. How do you stop that?
Well, this is where the MDN-RNN's probabilistic nature comes in handy again, along with that temperature parameter.
Right, making predictions less certain.
Exactly. By predicting a distribution of possible outcomes and by tuning the temperature to add a bit more randomness, the dream environment becomes less deterministic, less predictable.
Harder to game the system.
Right. It makes it harder for the agent to find and rely on those specific exploits that only work because the model is flawed. They included results showing how different temperature values affected performance.
What did they show?
There's a trade-off. Lower temperatures might make the dream easier to exploit, but potentially harder to learn general strategies in. Higher temperatures make it harder to exploit, but might also make the simulation too chaotic to learn effectively. Finding that sweet spot is key.
So managing the uncertainty in the dream is crucial. The paper also briefly mentions an iterative training procedure for harder tasks.
Yeah, for really complex problems, just one cycle of model building and controller training might not cut it.
Makes sense.
So the iterative idea is the agent explores the real environment a bit to gather some initial data. Train the world model on that. Train the controller in the dream. Then use that controller back in the real world to explore more effectively, gathering better data, especially from tricky situations.
And then you use that new data to refine the world model.
Exactly. Refine the model, retrain the controller in the improved dream, go back to the real world. You repeat this loop. The agent's understanding and policy gradually get better and better.
And they suggested using the model's own prediction errors as motivation.
Yeah, a really neat idea. If the world model is consistently wrong about predicting what happens in a certain part of the environment, that signals that the agent doesn't understand that part well. So you can use that prediction error as an intrinsic motivation signal, encouraging the agent to actively explore those poorly understood areas to get more data.
Wow, so the AI becomes curious about what it doesn't know. That's clever.
It is. And they even draw a parallel to neuroscience, specifically findings about hippocampal replay in the brain, how we seem to replay experiences, especially surprising ones, to consolidate memories and learn. This iterative refinement feels analogous.
A fascinating link between AI research and how our own brains might work. Okay, so that's a deep dive into the Ha and Schmidhuber paper. What about the Forbes article? How does it connect?
The Forbes piece broadens the perspective, looking at how this world model concept is influencing generative AI and large language models, LLMs, more generally.
Okay.
It uses a nice analogy, learning about baseball. You can read all the rules, stats, history that's like the massive text data an LM trains on,
Right, the knowledge base.
but then actually going to a game, watching the dynamics, seeing how plays unfold in real time, that gives you a much deeper, more intuitive understanding.
Ah, the experiential part.
Exactly. And that's where world models come in for AI, according to Forbes. It's like giving the AI a way to get that experience.
So instead of just text, maybe the AI interacts with like a baseball video game simulation.
Precisely. Or a driving simulator for a car AI. These virtual environments act as world models, allowing the AI to gain experience that supplements or grounds the symbolic knowledge it got from text data.
So it reinforces the paper's findings about training and simulation and transferring to reality, but applies it more broadly.
Yes, it connects that core research idea to the push for more capable and grounded generative AI systems.
Does Forbes also mention the downsides? Like the cheating the model problem?
It does touch on the limitations. It acknowledges that these world models are, by nature, incomplete. They're simplifications, and they can contain errors or biases.
And the AI might learn those errors.
Potentially, yes. If the simulation has flaws, the AI might learn strategies that only work within that flawed simulation.
Right.
But Forbes also heavily emphasizes the huge advantage of using these virtual world models: safety and cost.
Yeah. Makes sense.
You can run millions of experiments, test countless scenarios in simulation without any real-world risk or expense. The article uses self-driving car AI development as a prime example.
You can simulate crashes and near misses endlessly without actually crashing anything.
Exactly. It dramatically accelerates development and testing in a safe way.
Okay. Did Forbes raise any other big questions?
It posed an interesting one. How many world models does an AI need? And what kind should they be?
Like, should a self-driving car AI have separate models for weather, traffic patterns, pedestrian behavior?
Maybe. Or maybe one giant integrated model. There are big trade-offs in development time, computational resources needed to build and run these models versus the potential benefits in performance and safety. It's an open question.
A design choice for future AI systems. Okay, that brings us to the third source. The NVIDIA glossary entry on World Foundation Models, WFMs.
Right. NVIDIA, being heavily involved in AI hardware and platforms, especially for things like robotics and autonomous vehicles, has its own take. They define WFMs as these large neural networks trained to simulate real-world environments, often generating video output.
Simulating reality as video.
Yeah, and they can predict outcomes based on various inputs. Could be text prompts, images, existing video clips, sensor data.
And they specifically mentioned developers using these WFMs for physical AI, robots, self-driving cars.
Yes, primarily for generating high-quality synthetic data, training data created by the model rather than collected expensively from the real world.
Okay, so it's a tool for generating training material. Do they break down different types of WFMs?
They do. They talk about prediction models. These generate continuous motion, like predicting how a traffic scene will evolve.
Okay.
Style transfer models. These can take structured input, like maybe raw LiDAR data from a car.
The laser scanner points.
Right. And use that structure to guide the generation of photorealistic video of that same scene.
Wow, okay, so turning sensor data into a realistic movie.
Essentially, yes. And third, reasoning models. These analyze spatial and temporal details, cause and effect within the simulation to help an AI make better decisions.
So understanding the why behind this simulation. Got it. Do they give examples of where these are used?
Yeah, two main ones. Autonomous vehicles. WFMs generate diverse scenarios, different traffic jams, sudden weather changes, rare edge cases to train the entire AV software stack and drastically speed up virtual testing.
Makes sense, catching those rare events safely.
And robotics. WFMs create photorealistic synthetic data to help robots develop spatial intelligence, understand object interactions, and practice complex tasks safely in simulation before trying them in the real fragile world.
Okay, so what are the big benefits NVIDIA highlights for these WFMs?
They list several. Realistic video generation, but with a deeper understanding of cause and effect than older methods. Predictive intelligence, allowing the AI to sort of imagine different future scenarios based on current actions.
Like the dream learning.
Exactly. Improved policy learning, helping the AI figure out the optimal sequence of actions. And overall optimization, simulating resource usage, efficiency, feasibility of tasks before deployment.
So quite a powerful toolkit. How does NVIDIA say these big models are actually built? What goes into them?
They stress the need for absolutely massive amounts of real-world data, especially video data, as the foundation.
Data, data, data.
Always. Then these huge neural networks, often with billions of parameters, learn an internal representation of that data, capturing the patterns and dynamics of the environment. And it's a continuous process. Deep learning techniques constantly refine the model as more data comes in or as it's trained further.
Are there specific steps they mention in building them?
Yeah, they outline a few key components. Data curation, critically important.
Yeah.
Filtering, annotating, classifying, deduplicating all that multimodal data to ensure it's high quality. Garbage in, garbage out, right?
Right. Quality matters as much as quantity.
Tokenization, breaking down the input data, especially visual data, into smaller manageable units or tokens for the model to process efficiently. These can be discrete tokens or continuous ones.
Okay, digesting the data.
Fine-tuning. Often you start with a massive pre-trained foundation model and then adapt it, fine-tune it for a specific task or domain using techniques like unsupervised or supervised learning.
Specializing the general model.
And reinforcement learning, particularly for those reasoning models, training them through interaction with a simulated environment, using rewards and penalties to guide their learning towards desired behaviors.
Learning by doing within the simulation.
Exactly. And NVIDIA, of course, mentions their own platforms like NVIDIA Cosmos and Isaac GR00T, which are designed to facilitate building and deploying these kinds of world foundation models for physical AI.
Okay, so putting it all together then, from the original paper to Forbes to NVIDIA, the big picture seems to be this shift. AI isn't just learning from static data sets anymore.
Right. It's learning to understand and interact with the world by building these internal, dynamic, predictive models of reality itself.
Like developing its own intuition about how things work.
You could frame it that way. And the potential here is pretty huge, isn't it?
It seems like it. This could genuinely accelerate how we develop more capable, more adaptable AI across so many areas.
Absolutely. From safer autonomous vehicles, like we discussed, to more dexterous robots in manufacturing or homes, maybe even more sophisticated and grounded generative AI that understands context better.
For me, the real aha moment, the thing that sticks, is that idea from the paper successfully training an AI agent inside its own dream and having that knowledge transfer effectively to the real world.
Yeah, that's powerful stuff.
It feels like a potentially much more efficient, maybe even more scalable way to build intelligence compared to just brute forcing learning in the real world or with static data alone.
It definitely offers a compelling alternative path. But we should also remember this isn't solved science yet, right?
True. What are the big hurdles still?
Well, there are ongoing challenges. Building world models that are accurate and complex enough to capture truly intricate real-world dynamics is hard. Model capacity is still a limitation.
Making the dreams detailed enough.
And preventing that cheating issue, ensuring agents don't just exploit model flaws instead of learning robust strategies, that requires careful model design and training.
Right. Making the simulation good but not gameable.
Plus, developing better iterative training methods. How do you best guide the agent to explore, gather the right data, and refine its model and policy effectively, especially for really long horizon tasks? Lots of active research there.
So still plenty of work to do. But it really leaves you wondering, doesn't it? As AI gets better and better at simulating our world, maybe even worlds, what new possibilities open up? And what new ethical considerations might pop up from having these artificial agents learning, operating, maybe even making decisions within their own complex simulated realities?
That's a deep thought to end on. The implications of AI having its own mental models, its own internal worlds, it's definitely something we'll need to keep exploring as this field evolves.
Absolutely. Well, this has been a fascinating deep dive. Thanks for unpacking all that with me.